This video focuses on problems related to thermal expansion, solids, and liquids. So, students and friends, stick around, watch and learn. The first question, question number 1. A ball made of metal X has a diameter that is slightly greater than the diameter of a hole that has been cut into a metal plate made of metal Y. The coefficient of linear thermal expansion of metal X is greater than that for metal Y. Question is, which one or more of the given procedures can be used to make the ball pass through the hole? So as shown in this diagram, initially the ball has a bigger size. Its diameter is slightly greater than the diameter of the hole of this metal plate. In other words, the ball will not pass through uh, the hole, all right, initially that is. So our goal is we want the metal ball to be able to pass through the metal plate. So which among these given procedures can be done so that the ball will be able to pass through the hole? So option letter A, raise the temperatures of the ball and the plate by the same amount. Option letter B, lower the temperatures of the ball and the plate by the same amount. Letter C, heat the ball and cool the plate. And option letter D, cool the ball and heat the plate. Okay. The correct answers are option B is correct and option D. Alright? So, the concept that is applied here is the fact that a hole in a flat metal plate expands when the metal is heated. Okay? Just as a piece of metal the same size as the hole would expand. So, letter D is quite obvious. Okay? If you're going to cool the metal ball, its final volume will be smaller, all right? Smaller compared to the volume of the hole in the metal plate. So that would allow the ball to pass through the hole. Letter B, likewise, can be explained. Okay, it's quite similar to letter D because if you're going to lower the temperature of the ball, its final volume will be smaller. And since the plate will also be cooled down, in other words, its final volume will also be smaller, okay, compared to its original volume. That goes through also with the hole. But since the thermal coefficient, all right, of metal X is greater than that of metal Y, all right, uh, their what we call this change in volume will not be the same, all right. Um, as I said, the final volume of the metal ball when it is cooled, okay, will be much smaller than the final volume of the metal plate. Alright? So, naturally, the metal ball will be able to pass through. This will be explained further and will be proven by quantitative analysis and computations in the succeeding problems. Question number 2. Aluminum rivets used in airplane construction are made slightly larger than the rivet holes and cooled by dry ice or solid carbon dioxide before being driven. If the diameter of a hole is 4,500 millimeters, what should be the diameter of a rivet at 23.0 degrees Celsius if its diameter is to equal that of the hole when the rivet is cooled to negative 78 2.0 degrees Celsius, the temperature of dry ice. Assume that the expansion coefficient of aluminum, alpha, is equal to 2.4 raised to the negative 5 per Celsius degree, remains constant. Alright, so our solution to this question is to apply the concept that the change in length, alright, of any elongated material, okay, is dependent. In fact, it is directly proportional to its original length L naught and to the change in temperature. Alright? So when materials are heated, we know that they do expand. And specifically, the change in length is affected by, of course, the change in the temperature, and it also depends on what its original length is. This can be translated into a simple equation, delta L, which is also L minus L naught, being equal to a constant known as the coefficient of linear thermal expansion of the material multiplied by the initial length and the change in temperature delta T. Alright? So, we are going to apply this equation to the diameter D of the rivet. Alright? That simply means we're just changing the notation. Instead of L for length, we're going to use D for diameter. Alright? And for simplicity, I am going to let the initial diameter to be equal to 4,500 millimeters. And our goal is to determine the final diameter. Alright? This corresponds to assuming that our initial temperature, alright, is that of the lower temperature. Okay? So we will see this in our substitution to this formula. But before that, we first determine the change in temperature. So this is exactly what I meant. Delta T, which is defined as the final temperature minus the initial temperature. Okay? 23.0 degrees Celsius is the final temperature minus the initial, which is negative 78.0 degrees Celsius. Alright? This initial temperature, negative 78.0 degrees Celsius, is the corresponding temperature of the material with an initial diameter of 4,500 millimeter. Alright? So, the change in temperature 101.0 degrees Celsius, alright, is what we're going to use in this formula when we substitute the given data. Alright? So, D naught, which is 4,500 millimeter multiplied by quantity 1 plus the value of alpha, 2.4 raised to negative 5 per Celsius degree. That would be multiplied first by the change in temperature delta T before that will be added to 1. Alright? So simplifying, we get as the value for the final diameter equal to 4.511 millimeters. Alright? So, this is the answer to our question. Alright? Our solution is just one of two possible options that you can take. You may also let the initial temperature, alright, the initial temperature to be 23.0 degrees Celsius instead of what I chose, which is negative 78. All right. So if you choose the initial temperature uh, being 23.0, your what you call initial diameter is what you're going to determine. All right. But nevertheless, okay, you will still arrive at the same value for uh, the final diameter, all right? The one that we got here, 4.511 millimeter. So probably you can try that also, all right? You can let the initial diameter to be the unknown, all right? The unknown variable, because the problem actually uh, specifies that the uh, initial diameter of the material is not yet given. This 4.500 millimeter is actually the final diameter, all right, of the material. It's just that for simplicity, all right, I just chose this consideration, and this is what I got. So you can check this, okay, by doing my suggestion. All right. Question number 3. A machinist bores a hole of diameter 1.35 centimeters in a steel plate at a temperature of 25.0 degrees Celsius. What is the cross-sectional area of the hole at 25.0 degrees Celsius? So that is question letter A. Question letter B. What is the cross-sectional area of the hole when the temperature of the plate is increased to 175 degrees Celsius? Assume that the coefficient of linear expansion remains constant over this temperature range. So we're taking the value of the linear expansion constant alpha for steel equal to 1.2 times 10 to the negative 5 per Celsius degree. So our solution will still be applying the same concept, but this time we're talking about um, change in the area, all right? Where capital A stands for the area of the hole at a higher temperature, all right? While A naught is the initial area when the temperature is still uh, low. In the problem, the initial is 25.0 degree and the final temperature is 175 degrees Celsius. All right. Now, the coefficient of linear expansion, alpha, will be multiplied by 2. All right. So that is what we do whenever we are uh, using this coefficient, all right, in determining change in the area. Of course, multiplied by change in temperature. So, in answer to letter A, we first determine the value of the initial area of the hole, A naught, okay, using the formula for area, pi r squared. So pi multiplied by 1.35 centimeter divided by 2 because this is the given diameter initially, right? Then we get the square, and what we get is A naught equal to 1.43 centimeter squared. For determining the final area of the hole, okay, we will first determine the change in the area, delta A, and that is the difference between A final minus A naught, all right? And substituting or using this definition of delta A, which is twice the alpha multiplied by the initial area A naught times delta T. Substituting the data to this formula, okay, we have 2 multiplied by the value of alpha and the computed A naught, 1.43 centimeters squared, okay, and change in the temperature, 170 degrees Celsius minus 25.0 degrees Celsius, we will get the value for delta A equal to 5.15 raised to the negative 3 centimeter squared. All right. So we can now answer letter B. Okay, what is the final area of the hole, capital A? We simply add the change in the area that we got here, all right, plus the initial area of the hole, or A naught, that is 5.15 raised to the negative 3 centimeters squared, all right, plus the value of A naught, 1.43, and we will get the final value for area of the hole equal to 1.44 centimeters squared, all right. So you will notice that the change in the area is just very slight, very small, right? Even if the temperature change is quite large. We are down to our last question, question number 4. A steel tank is completely filled with 2.80 meter cube of ethanol when both the tank and the ethanol are at a temperature of 32.0 degrees Celsius. When the tank and its contents have cooled to 18.0 degrees Celsius, what additional volume of ethanol can be put into the tank? We use the volumetric thermal coefficient. For ethanol, beta is equal to 1.1 raised to the negative 4 per Celsius degree, while for steel, beta is equal to 3.6 raised to the negative 5 per Celsius degree. All right, our solution, we still apply the same concept, but again, this time we are talking about change in the volume. All right, so delta V is equal to V naught multiplied by the constant beta times delta T. All right, so we begin with the change in volume for the steel tank, delta V sub S. All right, so substituting in the formula, 2.80 meter cube, this is the initial volume of the steel tank, although it's mentioned in the problem that that is the volume of ethanol. But since the tank is filled with that amount of ethanol, it follows that the initial volume of the steel tank is also 2.80 meter cube. All right? So when we multiply this by the value of beta for steel, which is 3.6 raised to the negative 5 per Celsius degree, and the change in temperature, all right, it is negative 14.0 Celsius degree because in the problem, the final temperature is 18.0 degrees Celsius while the initial is 32.0. So when you get the difference, final minus initial, this is what we get, negative 14.0 degrees Celsius. Doing our math, we will arrive at value of delta V for steel tank, and that is equal to negative 1.41 raised to the negative 3 meter cube. In liters, that is equivalent to negative 1.41 liter. The negative sign suggests that we have a decrease in the volume, right? Now, knowing that this is the change in the volume, okay, we can also determine the final volume of the steel tank, all right? Vs. And this is just adding this delta Vs in meter cube, negative 1.41 raised to the negative 3 meter cube. We add this to our initial volume, which is 2.80 meter cube, and we will get, okay, the final volume for the steel tank equal to 2.799 meter cube to 4 significant figures. All right. Now, next, we will also apply the same procedure or computation for determining the change in the volume of ethanol. All right? The same formula, we just change the value of beta, substituting 2.80 as the initial of V naught, 2.80 meter cube, and the value of beta for ethanol is 1.1 times 10 to the negative 4 per Celsius degree. Again, the same change in temperature, negative 14.0 Celsius degree. So doing our math, we will get delta V for ethanol equal to negative 4.31 raised to the negative 3 meter cube, which in liter is equivalent to negative 4.31 liter. So just like what we did earlier for steel tank, all right, the volume of ethanol, all right, at a lower temperature, all right, V's of E, all right, V's of E 2.796 meter cube. This is determined by also adding, all right, the delta V for ethanol, negative 4.31 raised to the negative 3 meter cube, plus its initial volume, 2.80 meter cube. This is what we get, all right? So, as you can see, comparing the final volume of the steel tank with that of the ethanol, all right, there is quite a slight difference, all right? Slight difference in the change in volume, but obviously the final volume of the steel tank is a little greater than that of ethanol, all right? So what does that mean? There is still a certain volume of the tank that is empty, all right? And to determine that, that is exactly what is asked in the question. What additional volume of ethanol can be put into the tank, all right? We determine that by just subtracting, all right, the computed delta V for ethanol in liters, that is negative 4.31 liters, minus that of the steel tank in liters, we have negative 1.41 liters. So what we get is the value negative 2.90 liters. All right. So what does this mean? This is the amount of ethanol that can still be added, all right, to the steel tank so that it will also be completely filled just like what it had initially, all right? 2.90 liters of ethanol can be added. You can also check, instead of using the volume in liter, you can also determine this amount of ethanol that can be accommodated by also subtracting, all right, by also subtracting the what do you call this, the delta VE, all right, in terms of meter cube, all right, negative 4.31 raised to the negative 3 meter cube, that's for ethanol. You will still get the same value. Or, in short, another way is look at the difference between the final volume, all right? So just get that difference, 2.799 meter cube for the steel tank minus the final volume for the ethanol, 2.796 meter cube. And the difference, all right, in meter cube, all right, when converted to liter, that will still amount to almost the same as 2.90 liters. In fact, you will get 3.00 liter. All right, so that's one way of checking this answer. So that's it. We were able to answer the question for problem number 4. Thank you very much and hope to see you in our future video tutorial. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.